What is the Higgs boson? The Higgs boson is often called the God particle, a nickname that has captured the public's imagination. While many physicists dislike the term, it reflects the particle's importance in our understanding of the universe. To see why, let's ask a simple question. Why does matter have mass? In the mid-20th century, physicists built a theory known as the Standard Model of particle physics. This framework explains how fundamental particles and forces interact. It describes electrons, quarks, neutrinos, and the forces that bind them. Yet, the Standard Model originally predicted that many particles should be massless. If this were true, atoms could not form, chemistry would not exist, and the universe would look nothing like the one we see. In 1964, physicists including Peter Higgs, François Englert, and several others proposed a solution: an invisible field filling the universe, later named the Higgs field. Particles acquire mass by interacting with this field, just as objects moving through water experience resistance. The stronger the interaction, the heavier the particle. The Higgs boson is the quantum particle linked to this field. It is not the field itself, but rather a ripple, a detectable signature that proves the field is real. For decades, scientists suspected it existed, but lacked the technology to confirm it. That changed with the construction of the Large Hadron Collider, LHC, at CERN, the world's most powerful particle accelerator. In 2012, nearly half a century after it was first theorized, the Higgs boson was discovered. This confirmed not only the Higgs field, but also the Standard Model's explanation of mass. The discovery was celebrated worldwide and earned Higgs and Englert the 2013 Nobel Prize in Physics. The Higgs boson may not make headlines daily, but its importance cannot be overstated. It explains why matter has weight, why stars form, and why we exist at all. Without it, the universe would be a void of energy, incapable of supporting life. The Standard Model, the blueprint of particles. To appreciate why the Higgs boson matters, we need to step back and look at the Standard Model, the grand theory that describes the fundamental building blocks of the universe. The Standard Model divides particles into two families: fermions, which are matter particles, and bosons, which are force carriers. Fermions include quarks, which combine to form protons and neutrons, and leptons, such as electrons and neutrinos. Bosons, on the other hand, mediate interactions: photons for electromagnetism, gluons for the strong nuclear force, and W and Z bosons for the weak nuclear force. This model is incredibly successful. It explains how atoms form, why the sun shines, and how radiation interacts with matter. It has been tested in countless experiments, and its predictions are remarkably accurate. Yet, despite its success, it had one glaring flaw. It could not explain why particles have mass. For example, according to the early Standard Model, the W and Z bosons should be massless, but experiments showed they are extremely heavy. The electron, too, has a mass that allows it to form atoms. Without an explanation, the entire model was incomplete. This is where the Higgs field comes in. By interacting with the Higgs field, particles acquire mass. The photon does not interact and remains massless, while the W and Z bosons interact strongly, making them heavy. The Higgs boson itself is the proof of this mechanism. The discovery of the Higgs boson was therefore not just the discovery of a new particle. It was the final confirmation that the Standard Model is correct. Without it, the entire framework would collapse. Still, the Standard Model is not the ultimate theory. It cannot explain dark matter, dark energy, or gravity. It does not unify all forces under one law. In a sense, the Higgs boson both solved one of the deepest mysteries in physics and revealed just how many mysteries remain. The Higgs field, an invisible ocean. To understand the Higgs boson, we must first grasp the Higgs field itself. Imagine the universe as a vast, invisible ocean of energy. Every particle must travel through this ocean, and depending on how strongly it interacts with the water, it gains weight. This is essentially what the Higgs field does. It is an invisible, ever-present field that permeates all of space. Different particles interact with it in different ways. Photons, for instance, pass through without interacting at all, which is why light is massless and travels at the cosmic speed limit. Electrons, however, interact weakly, gaining a small mass that allows them to form atoms. Quarks, which make up protons and neutrons, interact more strongly and therefore become heavier. The Higgs boson is the quantum particle associated with this field. In physics, every field has a corresponding particle: photons for the electromagnetic field, gluons for the strong nuclear field, and so on. The Higgs boson is the evidence that the Higgs field exists. The importance of this mechanism cannot be overstated. Without the Higgs field, particles would have no mass, atoms would not exist, and the universe would be a soup of radiation and energy. There would be no stars, no planets, and no life. The Higgs field is not something we can see directly, but its effects are everywhere. Every object around you, your chair, your phone, your own body, has mass because of the Higgs field. It is a silent, invisible foundation of reality. The detection of the Higgs boson was like spotting a ripple on the surface of this invisible ocean. It was proof that the ocean itself is real. The Large Hadron Collider, the machine that found it. Discovering the Higgs boson was no easy task. It required building the Large Hadron Collider, LHC, the most powerful scientific machine ever constructed. Located at CERN near Geneva, Switzerland, the LHC is a circular tunnel 27 kilometers long, buried underground, where protons are accelerated to nearly the speed of light. The idea is simple: smash protons together at enormous energies and study the debris. At such extreme conditions, particles that don't normally appear in nature can briefly exist before decaying. By analyzing the results, scientists can detect new physics. The Higgs boson was predicted to be extremely heavy and unstable. It would decay almost instantly into other particles, making it incredibly difficult to spot. The LHC was built with the sensitivity to detect these rare events. Two major experiments, ATLAS and CMS, were designed specifically to search for the Higgs. In 2012, both teams announced they had independently observed a new particle consistent with the Higgs boson. The data was overwhelming. The long-sought particle was finally real. The LHC itself is a marvel of engineering. Its superconducting magnets operate at temperatures colder than outer space. Protons circulate 11,000 times per second, and detectors record collisions with precision smaller than the width of a human hair. The discovery was not just a scientific triumph, it was a global achievement. Thousands of scientists, engineers, and technicians from around the world worked together for decades to make it possible. The Higgs boson was the crowning jewel of the LHC's mission, but the collider continues to operate, searching for new physics beyond the standard model. The discovery, July 4th, 2012. On July 4th, 2012, physicists gathered at CERN for an announcement that would change science forever. Both the ATLAS and CMS experiments revealed that they had detected a new particle with a mass of about 125 giga-electron volts, GeV, exactly where the Higgs boson was expected to be. The room erupted in applause. Peter Higgs himself, then in his 80s, was in the audience, wiping away tears. After nearly 50 years, his prediction was confirmed. The discovery was so monumental that many compared it to the discovery of DNA in biology. The announcement was not just symbolic, it was based on hard evidence. Thousands of collision events had been recorded, and the statistical certainty was far beyond the threshold required for discovery. The Higgs boson was real. For the physics community, It was the end of one chapter and the beginning of another. The Higgs boson was no longer theoretical. It was measurable. Its mass, decay modes, and properties could now be studied in detail. The Nobel Prize in Physics was awarded the following year to Peter Higgs and François Englert. The prize was not just for predicting the particle, but for changing how we understand the fabric of reality. The Higgs discovery remains one of the greatest achievements in modern science. It showed humanity's ability to imagine, design, and build machines capable of revealing the deepest truths of the universe. Why mass matters. Building the universe. Mass is so familiar that we rarely stop to ask why it exists, but mass is the reason the universe has structure. Without it, matter would not clump together, gravity would not form stars or galaxies, and life could not emerge. The Higgs boson explains why mass exists. By interacting with the Higgs field, particles acquire weight. Without this mechanism, particles would simply fly around at the speed of light, never binding together. Take the electron, for example. Its tiny mass allows it to orbit protons and form atoms. If it had no mass, atoms could not exist. Quarks, too, owe their mass to the Higgs field, allowing protons and neutrons to form the building blocks of matter. Even the Sun depends on mass. Nuclear fusion in its core relies on the mass of hydrogen atoms to produce energy. Without mass, stars could not shine, and the universe would be dark and lifeless. The Higgs boson does not give all mass. Protons and neutrons gain much of their mass from the strong nuclear force binding quarks together. But the Higgs field is essential for giving mass to fundamental particles themselves. In a sense, the Higgs boson tells us why something exists instead of nothing. It explains why matter has substance, allowing the universe to evolve into the rich, structured cosmos we inhabit today. The Higgs and the early universe. The Higgs boson is not just about explaining mass today, it also has profound implications for the early universe. After the Big Bang, the universe was a hot, dense soup of particles and radiation. In the first trillionth of a second, everything was massless. Particles moved freely at the speed of light, and the Higgs field had not yet switched on. Then, as the universe cooled, the Higgs field underwent a dramatic phase transition. Like water freezing into ice, the field shifted into a new state, filling space and giving particles mass. This moment changed everything. It allowed matter to clump together, leading eventually to atoms, galaxies, and stars. Without the Higgs mechanism, the universe would have remained a formless soup of energy. The transition of the Higgs field was one of the most important events in cosmic history. Some theories even suggest that the Higgs field played a role in cosmic inflation, the rapid expansion of the universe fractions of a second after the Big Bang. While this idea is still speculative, it shows how central the Higgs field may be to our understanding of the universe's birth. By studying the Higgs boson today, physicists are essentially looking back in time, probing the conditions of the early universe. Every detail we learn about it may help explain why the cosmos looks the way it does. Beyond the Standard Model, unanswered questions. While the discovery of the Higgs boson was a triumph, it also raised new questions. The Standard Model is complete, but it is not the final word in physics. For one, the Higgs boson does not explain dark matter, the mysterious substance that makes up most of the mass in the universe. It does not explain dark energy, which is driving cosmic expansion. It does not unify gravity with the other forces. Physicists also wonder if the Higgs boson is alone or part of a larger family of Higgs-like particles. Some theories predict multiple Higgs bosons, each with different roles. Another puzzle is the Higgs boson's own mass. Why is it 125 giga-electron-volts? According to some calculations, it should be much heavier. Its actual mass suggests delicate fine-tuning, a mystery known as the hierarchy problem. The Higgs boson may also hold clues to why the universe prefers matter over antimatter. If matter and antimatter were perfectly balanced, they would have annihilated each other after the Big Bang. Something tipped the scales, and the Higgs might be part of the explanation. In short, the Higgs boson solved one mystery, but opened the door to many more. Higgs boson and the fate of the universe. One of the most dramatic implications of the Higgs boson concerns the long-term fate of the universe. The measured mass of the Higgs suggests that our universe may be in a state of metastability. This means the Higgs field is stable enough for now, but not absolutely permanent. Billions or trillions of years from now, a catastrophic event could occur, a quantum fluctuation that triggers the Higgs field to collapse into a lower energy state. If this happened, it would send a bubble of destruction expanding at the speed of light, rewriting the laws of physics as it passed. Atoms, stars, and galaxies would be obliterated instantly. While this sounds terrifying, it is not something to fear. If such an event occurs, it would be far in the distant future, long after stars have burned out. Moreover, new physics beyond the standard model may prevent it entirely. Still, the idea that the Higgs boson holds the key to the ultimate fate of reality is a sobering reminder of how deeply connected it is to the fabric of the cosmos. Conclusion. Why the Higgs matters. The discovery of the Higgs boson is more than just another chapter in physics. It is one of humanity's greatest achievements. It confirmed how particles acquire mass, completed the standard model, and gave us new insight into the universe's earliest moments. But its story is not over. The Higgs raises as many questions as it answers. Does it connect to dark matter? Is it stable forever? Are there more Higgs-like particles waiting to be discovered? For the public, the Higgs boson may seem abstract. You can't see it or touch it. Yet without it, you would not exist. Every atom in your body owes its mass to the Higgs field. It is not just a scientific curiosity. It is the reason for substance itself. The search for the Higgs boson shows what humanity is capable of. Thousands of scientists from across the globe worked for decades to imagine, build, and operate the Large Hadron Collider. They collaborated across cultures and borders, united by curiosity about the nature of reality. In a sense, the Higgs boson is not only the particle that explains mass, it is also a symbol of human ingenuity. It reminds us that even the most invisible, mysterious parts of the universe can be understood when we dare to ask questions and build the tools to find the answers. The Higgs boson is not the end of the story. It is the beginning of a new era in physics, one that may one day reveal the ultimate laws of nature.